Hello everyone. In this video, we shall discuss the fundamental trigonometric identities and we shall have examples that we prove some of the identities that will require the use of these fundamental identities. So first, let's recall that the trigonometric functions or the six trigonometric functions are defined in this manner using the right triangle approach. Now, if you notice, the sine and cosecant functions are actually reciprocals of each other. The cosine and the secant functions are also the reciprocal of each other, while the tangent and cotangent functions are reciprocals of each other. So which means we can define that sine of theta is equal to 1 over cosecant theta, or we can define that sine theta multiplied to cosecant theta is equal to 1. So the same thing goes with cosecant theta being the reciprocal of sine theta. So also, cosine can be written as 1 over secant, and secant can be written as 1 over cosine. And then cosine times secant is also equal to 1. Now, tangent can be written as 1 over cotangent, while cotangent can be written as 1 over tangent. And then tangent multiplied to cotangent is equal to 1. Now, another way of defining the six trigonometric functions is through the use of the unit circle. So if we have an angle theta having a terminal point equals x comma y, where this point lies on the unit circle x squared plus y squared equals 1, then we have the definition of the six trigonometric functions. So observe that sine and cosecant are reciprocals of each other, cosine and secant are reciprocals of each other, tangent and cotangent are also reciprocals of each other. So we can define the following reciprocal identities. So these are the six reciprocal identities, and then if we multiply those functions that are reciprocals of each other, then their products must be equal to 1. Now, another set of trigonometric identities here will be the ratio and Pythagorean identities. So if you notice, if we define sine theta as y and cosine theta as x, then the tangent theta, which is y over x, can be written as sine theta over cosine theta. So the same thing goes with cotangent of theta, which is x over y. So this means that cotangent can be written as cosine over sine. And that gives us the two ratio identities. And then, since we have x squared plus y squared equals 1 from the unit circle, we can write this as y squared plus x squared equals 1. And then we know that from the unit circle, the y coordinate of the terminal point is sine. So we can replace that by sine squared theta, while the x coordinate can be replaced by cosine squared theta or cosine theta. So thus we have sine squared theta plus cosine squared theta is equal to 1. So this is the first Pythagorean identity, or we call this the Pythagorean identity. Now there are two more Pythagorean identities that would result from this formula. If we are going to divide both sides of this equation by sine squared theta, we will be getting sine squared theta over sine squared theta, which is 1, plus cosine squared theta over sine squared theta, which is actually cotangent squared theta. And then 1 over sine squared theta would be cosecant squared theta. So we get the following identity. Now, if we are going to divide sine squared theta plus cosine squared theta equals 1 by cosine squared theta, then the resulting identity would be sine squared theta over cosine squared theta is tangent squared theta, plus cosine square theta over cosine square theta is 1. And then 1 over cosine square theta is equal to secant square theta. So we get this another Pythagorean identity. So the reciprocal identities, the ratio identities, and the Pythagorean identities will form the so-called fundamental trigonometric identities. So now, how are we going to use these fundamental trigonometric identities to prove some expressions? So in proving trigonometric identities, one may manipulate the left-hand side of the identity and show that it is equal to the right-hand side. Or it could be that we manipulate the right-hand side and show that it is equal to the left-hand side. Or we can manipulate both left-hand side and right-hand side and show that at some point that both sides are equal. Now, in manipulating these left-hand sides and right-hand sides, one might use the following techniques. So some techniques including identities would require us to write the expressions in terms of sine or cosine or both sine and cosine. Sometimes we multiply expressions on the left side or we multiply expressions on the right side. Sometimes if we have identities that would involve fractions, then we would be needing combination into a single fraction. Or sometimes if the expression in the left side or in the right side are factorable, then we have to factor those expressions. And also, in other cases, we might need to multiply the numerator and denominator of a fraction by an expression that is equal to 1 to produce a Pythagorean identity. Now, so let's have examples for proving identities. So let us prove the identity cosine x times cotangent x plus sine x equals cosecant x. So observe that this particular identity consists of cotangent and cosecant. So which means we can write cotangent and cosecant in terms of sine or cosine. So first, let's decide where to start first. Are we going to manipulate the left-hand side or the right-hand side? So it seems that the left-hand side has a longer expression than the right-hand side. So we can maybe start with the left-hand side. So left-hand side is cosine of x times cotangent of x plus sine of x. Now cotangent of x can be written in terms of sine and cosine using the ratio identity. We know that cotangent is cosine over sine. And then plus sine x. And then if we are going to multiply cosine x by this fraction, we will be getting cosine square x over sine x plus sine x. Now, since we have a fraction plus sine x, then we need to combine them into a single fraction with LCD equal to sine x. So if sine x will be multiplied to this fraction, that will give us cosine square x. And then if sine x will be multiplied with sine x, that will be sine square x. Now observe that cosine square x plus sine square x is the same thing as sine square x plus cosine square x. And by the Pythagorean identity, that sine square x plus cosine square x will just be equal to 1. So this gives us 1 over sine x. And we know from the reciprocal identities that 1 over sine x is equal to cosecant x. And this is our right-hand side of the equation. So this proves that the left-hand side and the right-hand side are the same. So that proves the identity. Okay, next. Let's prove the identity 1 minus cosine x times the quantity of 1 plus cosine x equals sine square x. So again, there's a product in the left-hand side. So we have to start with the left-hand side. That's 1 minus cosine x times 1 plus cosine x. So if you recall from algebra, a minus b multiplied by a plus b is equal to a squared minus b squared. So this product will now become the square of 1, which is 1, minus the square of cosine x, which is cosine square x. Now, from the Pythagorean identity, we know that sine square x plus cosine square x is equal to 1. So if we are going to transpose cosine square x to the other side, we will be getting sine square x equals 1 minus cosine square x. So that means 1 minus cosine square x can be replaced by sine square x. And this is the right-hand side of our identity. So this ends the proof of this particular item. Okay, next, let's try tangent to the fourth of theta plus tangent square theta equals secant to the fourth theta minus secant square theta. So it seems that in the left side, both terms has a tangent. In the right side, both terms has a secant. So which means in the left side, we can maybe factor out tangent square theta. So the second factor will be tangent square theta plus 1. While in the right hand side, both terms contains or has a factor of secant square theta. So we can factor secant square theta, and then the second factor will be secant square theta minus 1. Now from the Pythagorean identities, we know that tangent square theta plus 1 is equal to secant square theta. So which means that this thing here can be replaced by secant square theta. So the left side becomes tangent square theta times secant square theta. Now for the right side, secant square theta minus 1 can be replaced by tangent square theta. That is because from this identity, if we will transpose positive 1 to the other side, then we get tangent square theta is equal to secant square theta minus 1. So thus we have secant square theta times tangent square theta. And by the commutative property, this one is tangent square theta times secant square theta, or commutativity of multiplication. So this proves this particular identity. So observe that we manipulated the left side, we manipulated the right side, and then at some point, we prove or we have shown that both sides are the same. Okay, next. This time, let's prove 1 over 1 plus cosine x plus 1 over 1 minus cosine x equals 2 times cosecant square x. So observe that in the left-hand side, there are two fractions. So let's combine them first. Combining them, we get the LCD, which is 1 plus cosine x times 1 minus cosine x. And then this LCD here multiplied to the first fraction, we get 1 minus cosine x times 1, which is 1 minus cosine x. And then this LCD multiplied by the second fraction will give us 1 plus cosine x times 1. So we have plus the quantity of 1 plus cosine of x. So simplifying in the numerator, we have 1 plus 1, which is 2. And then the negative cosine x and the positive cosine x will cancel out. Now, all over, when you get the product of in the LCD, the product will be 1 minus cosine square x. And this thing, 1 minus cosine square x, can be replaced by sine square x by using the Pythagorean identities. And then this can be written as 2 times 1 over sine square x And we know that 1 over sine square x is cosecant square x, which is the right-hand side of our equation. So this proves our identity. Okay, next we have cosine x plus sine x is equal to cotangent x plus 1 over cosecant of x. So in this case, let's work on the right-hand side, and then we will replace that right-hand side in terms of sine and cosine. We know that cotangent x is cosine x over sine x, and then we have plus 1. Then cosecant x is 1 over sine x. Now, if we are going to combine the terms in the numerator, the LCD is sine x. Sine x multiplied to cosine x over sine x is cosine x. Sine x times 1 is sine x. And then denominator will still be the same. It's 1 over sine x. Now, this complex fraction may be simplified by multiplying the numerator by the reciprocal of the denominator. So this means that sine x will cancel out, and this will just give us cosine x plus sine x, which is our left-hand side of the identity. So observe here that we started with the right-hand side, we manipulated it, and then we have shown that it is the same as in the left-hand side. So this proves our identity. And then for this problem here, we have sine square x plus 2 sine x plus 1 over cosine square x is equal to 1 plus sine x over 1 minus sine x. So in this case, now if we notice this particular expression in the left-hand side can be factored as the square of a binomial. Because this one is like y squared plus 2y plus 1, where y is equal to sine x. So which means that it is a perfect square trinomial which can be factored as y plus 1 squared. So which means that if we replace y by sine x, that's going to be sine x and then plus 1 quantity squared over cosine square x. But since our goal is to show that it's equal to 1 plus sine x over 1 minus sine x, then we have to find a way of replacing cosine square x in terms of sine x. Now, by the Pythagorean identity, cosine square x is equal to 1 minus sine square x. So which means that this thing will be replaced by 1 minus sine square x. And in the numerator, the sine x plus 1 can be written as 1 plus sine x quantity squared. Now, the 1 minus sine square x is a difference of two squares. And it can be factored as 1 minus sine x times 1 plus sine x. And in the numerator, that's going to be 1 plus sine x quantity squared. It's still the same. So yung 1 plus sine x or 1 plus sine x will cancel out with 1 plus sine x quantity squared. So thus we get 1 plus sine x over 1 minus sine x, which is our right-hand side. Now, we can also use we can also prove this identity by using a different approach. If we are going to start with the right-hand side, okay, let's erase this first. If we are going to start with the right-hand side, we need to multiply both the numerator and denominator by, okay, so we start with the right-hand side. So that's going to be 1 plus sine x over 1 minus sine x. So we have to multiply this by 1 plus sine x over 1 plus sine x. So the reason for that is for the denominators to be multiplied similar to a minus b times a plus b, which is a square minus b square. So the reason for that is when you multiply them, that will just become 1 minus sine square x. And we can simplify 1 minus sine square x uh, as cosine square x by using the Pythagorean identity. Now in the numerator, we multiply 1 plus sine x times 1 plus sine x. So that's going to be 1 plus sine x plus sine x plus sine square x. So that's when we use the FOIL method, no, for this thing. So combining the middle terms sine x and sine x, we get 1 plus 2 sine x plus sine square x. And replacing 1 minus sine square x by cosine square x will prove the identity because this thing is our left hand side. Okay, so now we have shown all the techniques that were enumerated earlier. So the techniques are writing expressions in terms of sine or cosine, multiplying expressions in the left side or multiplying expressions on the right side, combination into a single fraction, factoring of expressions, and the last example required us, no, or uh, the last example may use this technique here of multiplying the numerator and denominator by an expression equal to 1 to produce a Pythagorean identity. So if you notice in the last example, we multiplied both the numerator and denominator by the same thing. But this one is actually equivalent to 1. Okay, so I hope that you learned something or you learned some of the techniques in proving identities from this video. And please don't forget to subscribe to my channel. Thank you for listening.